it's set by this leakage power. Okay? Meaning, can you... So here's the thing. So for instance, we know that from here, we know that it looks like it's roughly 3 times... It looks like it's the optimal supply voltage is roughly 3 times VTH. Okay, fine. Now, why don't we just decrease or scale VTH? If we scale VTH, then the supply voltage that we can run at is even lower, right? If it's, for instance, I don't know, if in 250 nanometer technology VTH is 500 millivolts, then this is roughly 1.5 volts optimally. But if we scale VTH to 200 millivolts, then this will be roughly what? 600 millivolts, right? So you can save more power. So the question here is that what is the limit? What stops you from scaling VTH? So it's what happens here, right? It's the fact that leakage has when sub-threshold, right, when VGS is 0, this has an exponential dependence. Leakage has exponential dependence on VTH minus VGS. So if this number decreases, this number shoots up exponentially. So eventually, it doesn't work. Okay. So you have to have some threshold voltage. You have to actually burn. Actually, optimally speaking, you have to have some threshold voltage. Do you understand? So the reason why you don't continue to scale VTH is because leakage current has an exponential dependence on VTH, okay? So that's why you don't scale it. Any questions? All right. Let's look at a little bit about transistor sizing. We talked about supply scaling. We found what looks like an optimal supply voltage in relationship with threshold voltage. We briefly discussed why we can't decrease threshold voltage continuously because of leakage power. Let's look at what happens in terms of sizing. How should you size gates optimally? So here's an inverter chain. Let's say these are loads. These are load capacitances. Okay? And looking into here, I see CG. Looking into here, I see CG. Okay? So this is a plot of the ratio of CG and CL in terms of energy and delay. And what you observe is that there's an optimal sizing of the inverter which minimizes the energy delay product. Okay? So for instance, in this simple example, if you say, so the delay is what? The delay, you can simply say it's R. It's R of this guy times what? CG plus CL. Right? So you can pull CG out. What am I doing here? CL, CG. Right? That's delay. And energy is what? Energy of this guy is actually CL B squared. Okay? So what you find out is that, so basically what happens is that, if you look at here, if CG is very, very large, that means what? What happens to the resistance? What happens to this resistance if CG is very large? Very small, right? So remember, when we talked about logical effort, right, there's two components. This component, if CG large, R is small, so this guy doesn't really change, right? But what's going to change is this guy. Okay? So the delay decrease, but what happens to energy? Energy increases, right? On the other hand, if CG is very small, this guy, the delay will increase. If CG is very small, the delay will shoot up. So naturally, just like the supply voltage, you also have an optimal point that relates the gate capacitance to the load capacitance, and that's roughly, when the ratio is roughly, in this case, about 0.5.
Question. Are you assuming that all the 4 gates have the same CG?
Yeah. Yeah. But the point, so the point that I'm trying to make is that even, so the importance of gate sizing, right? In terms of energy delay, which is a performance metric that you're trying to do. So when you're doing, for instance, if you really want to optimize a data path, it's something that you also have to look into carefully. Yes, you select the supply voltage carefully, but you also need to select the gate sizing carefully, okay, in terms of what it drives, okay? All right, let's talk a little bit about critical paths, and then I'll move on to some additional low power design tips. So this right here, so this is path count, this is a plot of path count versus delay. So what do I mean by path count? Path count, if you take a look at a processor, and then you just look at all the interconnects, all the interconnect lines, and you make a distribution of those interconnect lines in terms of the delay, you find that it has a distribution that looks something like this, okay? Meaning, some paths have small delay because they're what? Short. Some paths have larger delay because the interconnects maybe are larger, okay? And I'm just not talking about the interconnects, I'm talking about the data path itself, right? Through the inverters and so forth. Now, when you design a processor, you sell something with a target frequency. So this may be, for instance, 1 nanosecond. If this is 1 nanosecond, then your processor runs what? At 1 gigahertz, right? But you have a target delay, and you design it so that your processor meets the worst case. So what determines the speed of your processor? The slowest path, right? So these guys determine the maximum speed of your processor. But it doesn't mean that every single path in that processor will run at this speed. Some paths are running much faster. Do you understand? Okay? So here's the basic trick. The trick about low power design is that you know from all the previous discussions, what did you learn from the previous discussion? When I look at these things right here, where is it? Like here, what's happening here? If I change the supply voltage, if I decrease the supply voltage, delay shoots up. If I increase it, delay decreases. But at the same time, if I increase it, energy shoots up, and so forth, right? So, if you know, so basically, there's a trade-off between performance and what? There's a trade-off between performance and energy. You can trade off speed versus energy. Now back to this example right here. Okay. Now when you do a design, some paths are slower, some paths are faster. These are faster, these are slower. So the trick about low power design is that you can trade off the slow paths. You can trade off the fast path. You can actually make these paths slower on purpose to gain energy, to decrease energy. Do you understand? Because there's a trade-off between energy and performance, the goal is to actually intentionally slow down the fast paths and gain some energy. Do you understand? So what you want to do is basically push this guy so that the distribution is like this. In fact, the best case is if the distribution is an impulse here. You understand the basic trick? So if you have a slow path, then obviously the slow path is what determines the slowest path. The critical path will determine the ultimate speed of your processor. But the non-critical paths, the ones that do not determine the ultimate speed of your processor, those are the ones that you actually want to slow down. You want to make them more critical, but as you make them more critical, you're basically gaining energy. You're basically decreasing the energy of those paths. You understand? So that's the basic trick. So you want to downsize non-critical path. Okay? So there's basically no reward. You gain nothing. No reward from finishing computation early. In synchronous systems. Okay. So finishing early gives you no reward, except if you're doing homework for this class. Then it does. But, right? I mean, if this guy finishes early, it just has to wait. Okay? So the idea is that you want to finish late here. But by finishing, how do you finish late? The way you finish late is by maybe, what? Lower the supply voltage. Or maybe make the circuit smaller intentionally. Right? So that's the idea. So you want to narrow down the path delay distribution. Okay? Any questions? All right. So here, the low power design thing, the major way to reduce power is to rethink about the problem at the high level, right? Now, so that's the thing about trade-off, delay versus performance is ultimately what you are going for, okay? Now, a lot of low power comes from how you architect things. In fact, you get more improvement in performance when you rethink the architecture, right? Greater impact comes when things happen at the high level, right? You know, it's like if the school management decides to do something, it's going to affect all of us. The same thing with, you know, designing in a chip. Okay, if you change something about the architecture, those decisions, those changes are going to impact everything. Okay, so this is where your leverage is. There are two general techniques that will help with power, right? You want to reformulate the problem. So, for instance, if you assume that an operation needs 100 instructions, let's say anything, a job requires 100 instructions, and then you know your energy expended